Welcome to Power TV. In this video we'll explore one of the many capabilities of the design program Power 456, simulation. Hi, my name's Ridley, and in this program I'm going to compare the simulation capabilities of Power 456 with those of SPICE. Now there's many versions of SPICE available on the market. And probably the most popular these days is LT Spice. Everybody loves LT Spice because one, it's fairly easy to use, two, it really works quite well, and three, best of all, it's free and everybody likes that. So what we have here is a circuit in LT Spice. It's a flyback converter. Here you can see the primary of a transformer, secondary, and an extra secondary here forming the bias for the control chip. Our input voltage here is set at 200 volts DC, but the range is actually 90 volts to 240 volts AC. Output of the converter is 20 volts at 1.5 amps. That's a 30 watt power supply. Here we have the control chip, which drives the gate drive of a FET, and then the FET is running to a current sense resistor, and that's sensed by the current sense input of the control chip. Now let's go ahead and start running a simulation on this. So we go ahead, simulate, and run. And we'll choose some waveforms here, and you can see several waveforms on this converter are already running. The blue waveform is the control error voltage, the green waveform is the output voltage of the converter, and the red waveform is the output inductor, the second filter inductor on the flyback converter. That's part of a second stage filter used to attenuate noise. And immediately as you start the simulation, you can see some unusual things happening. First, there's an oscillation going on here, and then as the converter goes through a startup surge there, and over in this region here, again another oscillation, and it's not really quite clear what's causing this oscillation. It could be a numerical problem of PSpice, it could be something that really happens in the converter, or it could be part of the model that's been entered into PSpice. And that's one of the problems that you have with SPICE, is that you never really know whether it's a simulation problem or it's a problem that your converter really has. But let's keep that circuit running. Let's just make those waveforms nice and big here. And we're actually going to run this circuit for about 10 milliseconds. That's how long it's going to take for this output voltage here to climb up to about 20 volts. And you can see there it's hit maybe 6 volts so far, and it's on its way up. So while that's busy running, let's now go have a look at Power 456 and see how it handles this kind of simulation. And Power 456, you see I'm clicking on an Excel symbol here because it is actually an Excel worksheet that runs Power 456. And inside it, if we click on Start here, we see there's many things that it does. It helps us choose topologies, components, controllers. It does waveform simulation, control design, automatic feedback design. And there's many advanced features here as well for more advanced designers. There's a magnetics designer, snubber designer, second stage output filter. It does output filter analysis and also input filter analysis for your converter. So it's many things. It's not just a simulator, it's also a design program to help people who are beginning power supply designers or expert. And what we're going to do now is, here's our flyback converter. It's the same parameters as we put into LT Spice. And let's go click on waveforms over here, and we see some probes on the waveforms. So before we were looking at the output voltage. Let's go take a look at that. And this pulls up our screen to simulate the output voltage. Right now you can see the converter is already actually in steady state, but we want to go through and look up the startup. So first let's turn the time base here to look at a full 400 waveforms of operation, and let's go through a startup, as we're doing with LT Spice. And you can see how quickly this responds. Here's 1 millisecond of simulation already. If we want to do the same 10 milliseconds of simulation that we're doing with LT Spice, then we just click on continue, and each time you can see the simulation start time incrementing here. Now it's at 1.3 milliseconds, now 2.6, 3.4, I'm sorry, 4 milliseconds, 5 milliseconds, 6, 7, 8, 9, and there's our full 10 millisecond simulation. So you can see how fast this program simulates a converter. There's never any convergence problems because there is no convergence algorithm needed within Power 456. Let's go take a look now back at LT Spice to see how it's doing. And here we go, we've gotten up to 2 milliseconds so far, and you can see that this waveform is kind of painfully making its way up. If you look at the simulation speed, you can't quite see this probably on your monitors, but it's about 10 microseconds per second, which is about 1/500th the speed of simulation of Power 456. Now let's look at something else we could do with Power 456 while we're busy waiting, and click on line and load conditions, and what we can do is look at something like a step load condition in 456. So now we're stepping from 100% step for 100% load down to a 50% load. Hit OK, and we can see how quickly we see the overshoot in the voltage here, and it's really quite good for this design, for a little overshoot going in the output voltage. And we'll do some other things in a few minutes, but let's go have a quick check on LT Spice, see how it's doing. And we're up to 3.6 milliseconds here. And there's interesting things happening in LT Spice. You see that initial current surge there, way higher than the actual steady state current that we want to see in this converter. And again, it's not clear what's causing that. It could be the parameters weren't put in properly for the controller, or maybe this converter hasn't been designed very well and it truly does have this much surge. But as an experienced power supply designer, I certainly wouldn't want that to happen in my converter, because that's extra stress on the switch. That'll lead to premature failures. Alright, let's go back to Power 456 again. What else can we do in here? Let's stick with the simulation topic and look at the output voltage on the converter. And here we are again doing our simulation. Now let's get this back into steady state. 100% load, 100% load, right there. And sometimes when you're designing a converter, it's not exactly clear how you should choose all of your parameters. For example, the output L and the output C. You see here we have the opportunity to change these values of the capacitor and the inductor. So if I want to change my capacitor value, say to reduce the output ripple, I can just hit this little nudge button here, increase that capacitance, and you can immediately see a new simulation of 400 cycles showing you how the output ripple is reduced. I can reset that value back, and then I can change my inductor value. Let's go look at the inductor current before we do that, or the switch current. So it's a nicer way to look at the inductor. And here's my inductor current. You can see here something happening that's quite interesting. Let's zoom into that waveform a little bit by turning the time base. And there's a little bit of a step on the inductor current. So that means that I'm actually running this converter in continuous conduction mode. Not really sure I always want to do that. Some people want to keep it always discontinuous. It's not clear where this LT Spice design wanted to be. But suppose we wanted to force this into discontinuous mode, then all we do is reduce the value of the inductance. And by simulation we can immediately see when we hit the value of inductance that stops it being continuous conduction mode. And we can take that back to seeing the full simulation again. But you can see how very quickly the simulation is done. When I hit this button, it's less than a second before I see the peak current for 400 cycles of simulation. This would take a long, long time running this in Spice. Now, one thing that's happening here what's very interesting is when I change the inductor value for the simulation, the control loop is automatically being recompensated. So when I look at the transient response with the new inductor value, it's the transient response with the best controller on it that you can achieve. Let's go look at that with the output voltage step load. And that's right here. And let's do a bigger step this time, make it more interesting. Let's take it down to a 10% load, which is a pretty big transient on our converter. And what we see now is a lot of things happening, a lot of non-linearities come into the picture. This region right here, you can see there's no switching in the waveform, so the converter is just shut down when it drops down to 10% load, and it doesn't even bother switching until the output voltage has dropped to where it's supposed to be. If I hit continue on this waveform, we'll see a step load in the other direction. And here you can see the output voltage undershooting and then recovering back where it's supposed to be. Now the question, some people like to shrink down their inductor sizes to get a faster transient. Does that really happen? Well, let's try that. Shrink down the inductor further, and you can see indeed, you do indeed get a smaller overshoot with a smaller value of output inductor. Let's reset that back to the 100 microhenries that we started out with on LT Spice. And now we can see where we were before. Suppose you don't like this output voltage overshoot here, and you want to change the capacitor value. let's up that capacitor value. There's 170, that's 200 microfarads, 244, 292, that's 350 microfarads. So you can very, very quickly figure out what the right L, what the right C is for your converter. But again, remember, Power 456 is not just simulating this, it's redesigning the entire compensation loop to optimize around your capacitor and inductor values. When you run with SPICE, you try changing the L and C, you're going to get into a region where they're no longer optimum, and the controller won't work properly, and it'll be unstable, and then you're going to spend a long time going through the simulation process to even find out that that has happened. So let's shut that down for a minute. Now let's go have a look, see how LT SPICE is doing, and it's still kind of crawling up here. We're out to 7 milliseconds now, so we're 75% of the way. But it is simulating the converter for you. But we've got a little more spare time. Back to Power 456 if we want to. We've done some simulation here of the output voltage, the switch current. Let's go look at something different like the input capacitor. And this is an interesting thing to simulate because before I design my power converter, I need to know what the DC input voltage range is going to be. And I don't know that until I've run a simulation of the input bridge running into a capacitor. But of course that needs to know the power of the converter. So you've kind of got a little catch-22 loop here. But Power 456 lets us simulate that input voltage very, very quickly. So click on the rectifier there, and it pulls up a simulation of the input capacitor voltage and the input line current. And right now it's simulating an input voltage of 95 volts, and it's running a full wave rectifier. So you can see it's rectifying on both the negative cycle and the positive cycle of the input sine wave. We can change that if you like. If you want to change that to a half wave rectifier, just check the box there, and you see how much more droop you get here and the much higher peak currents that you get. Change that back to full wave again. Notice the simulation here is just basically instantaneous. And what's important from this simulation page is what is the bottom value of this input DC voltage. And that's 112 volts DC here. And what I really should do now is click on this button right here and use that minimum value for your design. So by simulating the input bridge, I now know my true input DC range, which is going to be 112 volts DC up to 373 volts DC for a 264 volt AC line. So now it's going to go redesign the capacitor, the inductor, the control loop, etc. for that minimum input voltage that comes from the simulation of the AC rectifier. Let's go have a look. Going to choose the topology again. We're still sticking with our flyback converter. Notice that within 456 you have many other topologies available to you, and you can actually take the same design and switch it over to a different topology and see how that simulates, but that'll be the topic of a different video. Let's go back to simulating some of our waveforms and look at the waveforms, the output voltage again, and let's get rid of our step load response here. Back to 100% step load. And just before we go take another look at this, let's see how LT SPICE is doing. And it's coming along here. It's just about at 9 milliseconds now. So we've got 1 millisecond to go. We can see we've almost reached the 20 volt threshold where the converter is regulating. And it's all looking fairly good. But you can see how much work we've been able to do in Power 456 versus what you're actually getting done here. This is simulating something that's already designed. Power 456 is designing something and simulating at the same time. So it's a much more powerful design tool than just this straightforward simulation tool that you have with SPICE. Let's go back to 456 again, look at some of the other things we can do in here. Here's our simulation. Let's continue this back to steady state after all those step loads have gone away. Okay, we've simulated the converter to steady state. One thing we can go look at now is the efficiency of the converter. And here we see we're coming out with an 87.35% efficiency. And it breaks it down for us into semiconductor losses, switching loss, conduction loss, magnetics winding loss, magnetics core loss, snubber loss, cap ESR loss, the control and the current sense loss for the converter. And we can use this to help us find out where the worst dissipation is, go change those components to see what happens to make our converter more efficient. Let's go have a look again at LT SPICE to see what's going on here. And there you go, you finally reached the simulated And it's not quite in steady state here. You see it overshot the 20 volts a little bit and it's coming down, and now the current is dropping down to where it wants to be. There's a transient going on at the end, so really you need to simulate this a little bit longer. But I think at this point you get the idea of what's going on here. The SPICE simulation is really quite slow compared to what 456 does, and it has no design capabilities built in. So this 456 really can help you when you're designing your switching power supply stages. Right at the beginning of the design, when you start with the spec, you put them into the program, and immediately you're getting simulated waveforms. In fact, when you run the converter, when you run the simulation program, all you need to do is enter your input specs and your output specs for the converter. You click OK, and it immediately designs the entire converter for you. It doesn't just run a simulation, it's choosing all the parts for you for whichever one of these topologies that you might want to use. So there is a brief overview of the simulation capabilities of Power 456. And if you watch our other videos, you'll be able to find all the other embedded features that are in there to help you with your power supply design. If you'd like to learn more about Power 456, please go to ridleyengineering.com and find out everything this program can help you do to accelerate your design process.